Let's consider rifles. When a soldier fires a rifle, what happens is he goes deaf. The concussive force of the bullets exiting the barrel produce severe damage to his hearing. It is too loud. There are 130 decibels or so, and that is way too loud for human hearing. It damages hearing, and it leaves you momentarily deafened. That makes you less efficient, less oriented, less capable of following instructions. If you reduce the noise of the rifles, the soldiers become more efficient. The Soviets produced two 9mm silenced assault rifles for special forces operations, the Val in the 1970s and the Vintorez in the 1980s. They were both based upon the Kalashnikov design. They could be fired semi-automatically or automatically. They typically were equipped with a sniper scope for silently killing people at least moderate distances. The 9mm bullet they used was not a traditional 9mm pistol bullet, but a much heavier 9mm rifle bullet. They were designed to be subsonic so that they could be silenced. When a bullet travels above the speed of sound, it produces a shock wave, which produces noise, which means it can't be silenced. The way it worked was you had the barrel. Past the point where the bullet accelerated to the velocity you wanted, there was an extension of the barrel with holes drilled in it. Off of those holes was a cylinder of metal with some diagonal baffle plates between the holes. So as the bullet moved down the barrel, the hole would be exposed. Pressure from the barrel would bleed off into the space in that annular cylinder. As the bullet traveled down the silencer, more of the gas would go into that annular space, draining the pressure inside the barrel. So when the bullet exited the barrel, the gases would make very little noise. They would be silenced. They were probably reducing the sound by at least 120 decibels. If one uses a much shorter silencer, a much lower level of reduction, the bullet exiting the barrel leaves a pressure of gas. If you use high explosive gases, energy values for high explosive are on the order of 18 to 22 million pound-inches per pound of explosive, which is something on the order of 1.5 to 1.9 pound-feet. Using the U.S. Common System, there's the constant need to use the acceleration of gravity, which is 32 feet per second. If there are massive explosives is detonated, it produces at least 1.5 million pound-feet of energy or more. You multiply by 32, that allows for converting the pound of explosive into mass. One multiplies 1/2 times the mass times the velocity squared to get energy. So it's 2 times 32, which is 64, and you get a number of somewhere over 100 million. So the normalized velocity squared, the average velocity of the gases in a vacuum would be about 100 million, and the velocity would be about 10,000, kind of averaged out. That gives you kind of a maximum idea of the velocity of gas. As the bullet is going down the barrel, the gas energy is accelerating the bullet, so there's less energy available to accelerate the gas. On the other end, the speed of sound is about 1,100 feet per second, about 340 meters per second. And if a barrel was even 2 feet long, it would take 1/500th of a second at the speed of sound, or about 2/1000th of a second. Most of the gas pressure is going to be exiting above that value in thousands of feet per second. So by the time the speed of sound is reached in the barrel, sound is a low pressure wave. Most of the gas pressure would have exited, which is 2/1000th of a second. So it's well under 2/1000th of a second, probably more on the order of 1,000th of a second for most of the gases to exit the barrel. The bullet is dissipating energy by traveling above the speed of sound. It takes a long time to do that. Bullets have long flight times. 2,600 feet per second, a bullet in theory has a maximum range in a vacuum of something on the order of 200,000 feet, or 40 miles, or 66 kilometers. Now, aerodynamic drag would greatly reduce that. If you allow for something on the order of 5 miles, 2,600 feet per second, that would be 10 seconds of flight time. That would represent a significant reduction in the energy of the bullet. The amount of energy that goes into the bullet is somewhere between 25 and 30% of the total energy. So the energy of the gas is over twice the energy of the bullet. If you look at 10 seconds in the order of thousandth of a second, you get a number of about 10,000. There's no point in reducing the muzzle energy below the sound of the bullet. Most of the energy from the propellants come out of the barrel in under a thousandth of a second. The bullet will take probably 10 seconds or more to slow down and lose velocity. So right there, you're getting a factor of something on the order of 10,000 between the energy of the bullet and the noise the bullet makes by producing a shock wave and the noise that is produced by the propellants exiting the barrel. The bullet, of course, has more energy loss when it leaves the barrel, traveling at a higher velocity as it slows down. Less energy will be dissipated at any time, so it'll become a little bit quieter. An increase in 10 in pressure is an increase of 20 decibels. So if there's a difference of even 1,000 between the pressure produced by the energy dissipation of the bullet and the energy of the propellant coming out of the barrel, that's 60 decibels. Reducing the sound from the propellants by 40 decibels won't even come close to the sound of the bullet. There's no point in making it obviously quieter than the bullet because the bullet will produce its sound. So it looks like the sound can be reduced somewhere between 30 and 40 decibels before the bullet noise exceeds the sound of the gases escaping from the barrel. If the assumption is made, the amount of reduction is proportional to the length of the barrel, so that each section reduces it by a similar amount in terms of fractional reduction. So for instance, it reduces it by 1/2, then the next length would reduce it by 1/4, 1/2 of 1/2, then reduce it by 1/8, 1/2 of 1/2 of 1/2. So each section is doing a 1/2 reduction from the entrance of the section to the exit of the section in terms of the silencer. Well, one would get 60 decibels, for instance, then 30 decibels, 15 decibels. 60 plus 30 would be 90, plus 15 would be 105. The next one would be 7.5, so up to 112. That's about the order. So 1/4 to 1/5 of the barrel length would represent 60 decibels of reduction. That's more than you need. So it would be something on the order of 1/8 of the length of the silencer used for the Vinteras would give you the 30 decibels you want to reduce. Now we get into barrel lengths, amount of energy in the bullet, the amount of energy in the gases. It wouldn't have to be particularly long, maybe something on the order of 10 centimeters or less, 4 inches extension at the end of the barrel. That might be enough to take 30 decibels off. A tenfold increase in pressure is 20 decibels. So every 20 decibels represents a tenfold increase in pressure. For every 10 decibels, pressure goes up 3 times. 120 decibels is 10 to the 6th, or a million times increase in pressure. A 30 decibel decrease is a decrease in pressure of over 30 times. So the pressure would drop to only 3% of the initial pressure. But there is a time delay. As the bullet passes by, the gas pressure has to flow through the hole into the chamber. There is only so much gas that can flow before the bullet reaches the end, if it's a short end. So it has to be long enough to give enough time for the pressure to flow into the annular ring and reducing the pressure in the barrel. But again, it shouldn't be more than a few centimeters. Now, that does mean you need a longer rifle barrel, a heavier barrel, and a somewhat more awkward, longer rifle. But it makes it much easier for the soldier to function with his rifle. It makes him more efficient as a soldier. As far as the operation of the gun, the tap hole that is used for a pressure-operated gun, which most guns are, that is operated before the end of the barrel. When the bullet reaches the end of the barrel, the pressure drops precipitously. The silencer is extended beyond that point, so the amount of pressure available to activate the piston rod or direct impingement system or however else the rifle works should still be perfectly functional, should not interfere with its operation. There is then the question of how far do you want to go? You could add this to things like the barrel of a tank. This represents a much longer and heavier barrel and might represent balance and weight problems, but it makes people easier to operate near the tank. You have personnel carriers. The U.S. personnel carriers have 25 millimeter cannons. Infantry are supposed to operate relatively close to them. You put a silencer on them, it's easier for infantry to work closer to the vehicles. And then we get into things like artillery. You put on an artillery piece, again, longer, heavier barrel. The artillery crewman would still have to wear hearing, but it might make it easier to work near the guns. And then, of course, we have mortars. One of the questions is that a mortar is designed to fold compactly. And if you have a big ring at the end, it makes it awkward to move the mortar and to store the mortar. And again, the mortar crews would still have to wear hearing protection, but it might just make it a little easier and a little bit more pleasant to operate the mortars. Pistols are a problem because pistols are designed to be compact, and any extension of the barrel or increasing the diameter of the barrel makes it difficult to store or wear a pistol. So that might not work. Handguns and rifles, it shouldn't be a problem. Other weapon systems could be problematic and may not be workable. The other effect it will have is to somewhat reduce the recoil. When the bullet exits the barrel, the gases rapidly expand, and that rapid change in momentum creates recoil of the gun. Having the gases in the annular cylinder and then released more slowly, it will have some effect of reducing the recoil of the gun. It's not a silenced gun, but it is a noise-reduced gun, and that should make it easier for soldiers to handle their weapons without going deaf.